Hello everyone. So I hope everyone is doing well. So yesterday I could not do the live stream because the problem of the daily lead code section was already solved by me. So the purpose of this session is to solve unseen problems, and this is today's problem is an unseen one. Probably it's hard, so we may or may not solve it. I don't know, but I'll try my best. Okay, so I think the live stream has started, and probably I'll be able to see some audio here. Let me refresh it and quickly check if everything is working well. Okay, we also got some viewer here. I don't know. This is today's problem is an unseen one. Probably it's hard. So we okay, so yeah, it works. Let's go and go to the question. So let me share my screen here. Um Here we go. I need to accept this and we are live. Okay, so let me grab my pencil and first quickly I will just outline how we are going to solve the problems. So the step one is to let me just use a temporary marker here, which is this one, right? So step one is about reading the problem. Okay. Step two is about step one is about reading the problem. Step two is about forming the initial approach. And step three is doing the time complexity analysis. And step 4 is actually doing the problem solving. So here we will go to the code editor and then we do the debugging part of it. So this, if you see, this is the entire approach. First I will read this problem, then I will do the initial logic building, and then after that we will do time complexity analysis, and if it fits the problem constraints, then we will go for coding section and we will code this problem. Okay, so this is classic lead code solving, and yeah, let me start it. So first I'm reading the problem. It says write a program to solve a Sudoku puzzle. So Sudoku puzzle by filling the empty cells. Okay, so there are some empty cells which we have to fill, and we have to solve the Sudoku puzzle. So Sudoku is a classical puzzle which we are kind of we see in newspapers everywhere, and it is there for a very long time. So we have to basically code it up how to solve a particular board. Okay, so a Sudoku solution must satisfy all of the following rules. So yeah, let's go through the rules. It's better to read all the rules first. First rule says each of the digits 1 to 9 must occur exactly once in each row. So let's say this is the row. So here each of the digits from 1 to 9 must appear once. Okay, so it means we can have 1 over here, then we cannot have 1 over here. So we can 1 over here, we can 2 over here, we can 3 over here, or 4, like that. Not 5 because 5 is already there. 3 is already there, so 3 will also not be there. So we can have 1, 2, 4, 6, 8, 9. So this is a valid row. This row is valid, but there can be more constraints. Let's go to that. Each of the digits 1 to 9 must occur exactly once in each column. So this is a column, right? And each of these digits, again for column as well, we have constraint that 1 to 9 should appear exactly once. That is something which we can think right now, that if I use 1 over here, then I have to also check that if 1 is not there already. So we cannot have 1 over here because 1 is already there. And third, each of the digits 1 to 9 must occur exactly once in each of the 9 sub boxes of the grid. So this is called a sub box, and there are 9 such sub boxes, and it says that each of these digits, like 1 2 3 4 5 6 7 8 9, so 6 cannot be twice here, so each of these digits 1 to 9 must appear exactly once in this board. Okay, and the character dot indicates empty cells. So this is something related to the grid. So this is the grid we have been given, the board which we have been given, and this means that the cell is currently empty. So this particular input translates to this visualization, which makes sense. Yeah, and then this is the output of it. So the question is clear to me. So we have been given a Sudoku board configuration, and we have to solve it and return the correct solution. Okay, so this is the logic. This is the not the logic. This is the problem which problem statement which we have to solve. So let's go to constraints. Board dot length is 9. That is obviously true. And board I dot length. So each row is having 9 such boxes. And then board IZ is a digit, which is 1 to 9, or it can be a dot. So input could be, so input is actually a string. So these numbers are actually strings. Now let's go ahead with the next constraint, which says it is guaranteed that the input board has only one solution. So this is, I think, guys, related to the Sudoku itself, because for each Sudoku, I don't think there could be multiple solutions. I have never played Sudoku, to be honest. So if you are like me, you can have a +1 in the chat. I don't know. I have never solved a Sudoku before, but I know the rules, and it is considered as a hard problem. But now let's talk about, so we are going to solve the Sudoku here, and let's talk about that since it is a hard problem. Like tic-tac-toe is a hard problem. For some matter, it is a hard problem when you try to automate it with the logic. So what happens in these games is that our next move, our next approach depends on the previous state. So there is a state linking. So these are classical DP problems. So if I talk about Sudoku, I think it is also one of those, because it is very unpredictable. Because if I try to have one over here, I have to check a lot of things here, like this. So, and here also, and this box also. So what I can do, if I don't try to solve it in DP way, I will take this particular block here, and we check what are the possible cases here. So for the, if I talk about this particular column, so it will give me cases like 1 cannot be used. Maybe the permanent marker here. So yeah. So this box, we cannot use 1 here. We cannot have 3. We cannot have 5. We cannot have 9. We cannot have 6. So you see 3, 1, 6, 5, 9. We cannot have these. And we cannot have 5, 3, 7. So 7 is the one more entry here. So what are we left with for this row? So the allowed input is this. We can have 2, we can have 4, we can have what, 6. Uh, wait a minute. Oh, yeah. So 6, we can have 6, we cannot have 6, we cannot have 6 here. So we can have 8. Yeah. So these are the allowed inputs, and I can use 2, 4, 8. It's up to me. So here you see there are 3 cases, 2, 4, 8. And if I do it in a logical way without using DP or caching, a brute force basically, uh, then I have to first put 2 and then move forward with the next steps. Then I have to put 4 and move forward with the next steps. So I'm saying this. So I will put 2 over here, and then I'll move forward with the next cell, and we will choose the value for this cell as well. And then this cell, what are the values? So you see, we first choose 2, and then we will choose, so for a particular cell, let's say we start from here. So our starting point, there will be a state with where we fill that box with 2, and rest other combination is there, like rest of the cell combination is there. So this will be a particular combination where we have filled the box with 2, and then there are 3 combinations possible at the first step, where we have placed 2 over there, we have placed 4 over there, and we have placed 8 over there. All of these three inputs create three different cases, right? And three different states. And then we move further with other cells. Let's say now we talk about this cell. So since first cell is filled with 2, now we have a different input configuration that is allowed for that cell. Okay, so that is the next step. So what other places it can take, we will define that in the array, and then we basically move forward with the next steps. Same goes for 4 here. So you see there is a lot of branching here, a lot of cases here. So if we try to have a common logic, so we have to either, like, if we have to try to have some greedy logic, then we have to crack it down. So we have to select here, like, which one is the best one. And I don't think uh, we can be biased with any of these numbers with any condition or something, because all of these seem equally important to me, because 2 can also be here, 4 can also be here, and 8 can also be here. Okay, so this is hinting me to move to a DP based solution. Okay, because whatever values this cell can take is dependent on what the values are currently in the state. Okay, so there are 9 to 9 cross 9, 81 cells, but for deciding an input for this cell, we have to check 9 plus 9 plus 9, 27 cells we have to check, and we check 27 cells here, and we fill the values over here. So let's see, in 27 cells, whatever number is not there in this set, that is the valid input for this cell. So that's the case. And if I talk about number of states, so essentially there are 81 such boxes. So we can say that there are 81 levels. So each cell could have its own value that could go from 1 to 9, possibly, yes. This can also go from 1 to n, apart from the cells which are defined earlier, already. Like, let's say 5 is here, then we don't need to think about what this cell can take. We can think only about these cells. So you see, like, at the worst case, entire Sudoku is empty. There we can have each cell, there we can have 81 cells, and 81 cells could take 1 to 9 values. So it is like 81 cells, and 9 is here, so 9 to the power 81. The combinations basically, if this cell can take 9 values, 9 values, 9 values, so how many combinations will be there for this entire grid? So it is first cell taking 9 values, second cell taking 9 values, likewise we go to 81. This comes out as 9 to the power 81 such states. So this is a very used number, probably exponential. 9 can be compared as 10, like for doing a hard calculation, not a exact calculation. So 10 to the power 81 is very huge. It will not fit in the current allowed brackets of allowed brackets of time limit constraints. So let's say if this problem was a tic-tac-toe, so where we had like 9 cells here, and these 9 cells, each cell could take 2 values, like to either cross or 0, or empty state, that is also there, a case there. So yeah, exactly, this cell can take, actually at a particular state it can take 10 values. First is 1 to 9 the digits, and then if it is empty, that is a dot. So it can take 10 values. So it is actually 10 to the power 81 such states will be there. Okay, in the worst case. Yeah, in the classical tic-tac-toe problem, so there also we have like 3 into 3 into 3. That was 3 to the power 9 states, which was still okay because it was in the time limit constraints. But 9 to the power 81 is really, really exponential. We cannot afford that kind of input. Okay. So first we have to solve this problem in a Sudoku way. So we kind of write what are the allowed configuration for these. The moment I choose 2 over here, cell configuration changes. So it is a very good problem, to be honest. And why it is hard, we all can sense that, because there are 10 states at each level, and it is 10 to the power 81, because these are having 81 cells in each grid. Each board has 81 cells. So how can we actually solve it? Even if we use DP, so for example, if we use DP, so that also goes step by step, state by state. So let's say this is a state, this will be the next state, this will be the next state. There can be crashing for sure. I agree, crashing will be there. But in the worst case, what will happen in case of DP as well is that we will be probably we will be right. So for DP, we will be basically let me think. Yeah, for DP we will be exploring all the possible states. That will be the worst case. Now let me think what could happen if we go in this way. Like we let's say for this 248 was the allowed input. So we select any of these and move forward. So will that result in a combination which is unsolvable? That is a very important thing to examine, guys. Without examining that, we cannot come. So let's try to solve this Sudoku ourselves. So I will, yeah, I will go with 2 for this part. Now let's come to this cell. So what are the acceptable inputs for this? So we can take 1 and we can take 2. No, we cannot take 2 because 2 is here. Yeah, then we go. Okay, so there is actually thunderstorm in my area. I'm not sure if you are able to listen to that. Sorry. So we have 1 over here. We have 2. No, we cannot take 2. We can take 3. No, we cannot take 3 because 3 is here. Can we take 4? We can take 4. For sure we can. Then we can take 5. No. 6. No. 7. No. 8. No. 9. Yes. So we have these 3 inputs here. And let's say we go with 1 here. So now I'll put 1 over here. For this, we will be left with limited options. Like now we have, so now we can, for this cell we can ask, so can we take 1, 2? No. Can we take 3? No. Can we take 4? Yes, 4 can be taken here. 5? No. 6? No. 6 is here. 7? No. 8? 8, yes. And 9? Of course, yes. So here we have the that is a good solution, but they say that there is exactly one solution, right? So if you remember, this board has exactly one solution. So if we select 2 over here, it might be the case we are exploring a longer side, which will definitely fail, right? We can be sure on this, that if we go with 2, there are high chances that this might fail. Okay, so there is no greedy solution as of now which I can think of. But to be honest, I'm directly jumping to the time complexity. Let's discuss the brute force here. So if I talk about brute force solution, first will be the go cell by cell, find possible values, and then for each value, sorry, oh my god, where has it displayed? Yeah, for each value, what we have to do is we have to, sorry guys, for each value we have to Go to the next state. Okay. Yeah, and then we come back and we do this. So brute force, I think, is very so we keep doing this unless all cells are filled. That's it, because we will be filling it optimally only. So unless all cells are filled, we can have this uh, thing here. Now I'm literally blank on how to solve this, because if we think using DP, which is memorization, which is caching, there will be 81 such boxes. And each box is equally legible to take 1 to 10 to 9 and start. So this is definitely the case, right? Each cell is equally legible to take these values. So this is clearly not the case. Uh, I don't think we can solve it like this. So what could be alternate approach? How can we decide that this cell will have two, nothing else? Because they say that it is guaranteed that input mode has only one solution. So we had three options here. So what logic we can use to select two over here? So yeah, we cannot have 10 to the power 81 dp. What extra can we have here is that we can focus on this part of it. If this cell is balanced, there also you can have multiple combinations now. Uh, if we focus on this cell, let's say here it is 2, so we can have 4 here, but 4 can be there. Yeah, we can focus on this cell, so it's more like 10,000 each. It will go like 10 to the power 9. This is also a very difficult case, to be honest. Honestly, I'm blank on this. Let me think more. How can we optimize? This is a very beautiful problem. Like we are not using 10 to the power 81 states. Instead, we found some greedy logic or some other solution. But greedy is really hard to crack here now. This is labeled as hard, and let me really think some hard approaches then. This will not help. These are very simple approaches, to be honest, which I was following right now. Okay, let me use a bigger circle to delete these. So where we stand currently, let's quickly examine that. So if we use brute force, forget about time complexity, it will never be met. If we use DP, there we are saying 10 to the power 81 states are possible. Now, if I talk about the other thing, which is greedy, which is not cracked yet. So what are the next step from this configuration is that we can do this, that we can look for optimized, let me call this highly optimized TP, or we can have a greedy solution. These are two steps which I can see currently. So we will explore these one by one. So I have no confidence with greedy because greedy is purely intuition based. That is that tells how you have solved problems previously, and then your mind will crack a logic which will solve. So greedy is currently out of scope at the moment. I will not jump into greedy, and it's kind of better to first go with brute force. Then also that will also actually help you to form a greedy approach if there is any. Okay, so Now there is one more thing here, which is basically the constraints of the problem. Sometimes they also hint us to use something, right? So if I see board length is 9 and 9, I can actually come to an approach where we have n to the power, probably n to the power 6. So n to the power 6 will probably work in this case, right? Or if we use kind of, let's say 81 is our n here, then we can have probably, let's consider this as 100. So we can have n cubed solution here. But given the values, the scope of the values, scope of each cell, it's really hard to think of that. So let's think what could be the cases. So we are uncertain about how many values this can take because that depends on the existing condition of the input. Oh, nice, nice, nice. So actually I was wrong, right? So it's not 10 to the 10 cases for each cell, like as we move ahead. So let's say we have filled this cell. So I think I have to take this example here. Okay, so let's choose a grid here. It's really crazy that we have exactly we have a grid here. Okay, so 1 2 3 4 5 6 7 8 9. Cool. So what I'm saying is that let's say this entire grid is empty, so this can take 10 values. Agreed? Now this part, when this is filled, this can take only 9 values. Yeah, we can leave this empty or we can fill it with something. Then we come to this cell. Yeah, let's talk about numbers only. So actually a correction here. Let me just delete this wisely. Okay. Okay. Perfect. So what I was saying that this can take 9 values, and this can take then 8 values. This will take then 7 values, and this will take 6. This will take 5. 3, 2, and 1. So I am definitely sure about this. This is like 9 factorial ways for going through this. And once we have filled this, we'll come to this cell. So here we are starting from 8, and here we are starting from not 8, actually not 8. So now this particular cell can take only, so since these three are filled, right? So this is left with only 6 values, to be very honest. Now this is left with 3 to 4. This is left with 5 values. This is 4. This is again when we come to this part, right? Here also 3 values are placed over here. 3 values are here. 6 values are already filled. This is 3. This is 2 because 3 values are here. Not actually. So this might can be same. Like this can be 1 over here. There can be 1 over here. That's fine. That's totally fine. So hard to predict this, but we can surely say that let's say 1 2 3 is here, 1 2 3 is here. This is the worst case. We can surely say that this can have 6 values at the worst case, right? Yeah, it can have 6 values at the worst case. Same goes for this. So it's like 6 5 4 here again, and then we come to this cell. So it can be possible that this exact configuration is replicated. So let's say there's 4 5 6. This is also 4 5 6, and it's still valid. And here, again, here we are left with how many values here? So this was 654. Now we have kind of six values filled for sure. So we can have 654, right? And we have six values filled. So this will be 3, starting from 3, then 2, and then 1. So 9 factorial is somewhat like 5 factorial is 120. Starts with these, and multiplied by 6 is, sorry, multiplied by 7. Uh, Probably, I'm not sure. 9 factorial is somewhat like, if we go to 8 factorial, this will be, uh, okay, so this is actually a multiplication, to be very honest. Here it is a multiplication. Which means that we multiply these guys, and then we multiply these guys as well. So if I actually, so I don't know guys, if you're able to see or hear those noises. Okay, so this is actually a multiplication, to be very honest. Here it is a multiplication. Uh, let's check that. By 4, right? And we have 6 values filled. This will be 3 starting 1. So the 9 factorial is somewhat like 5 factorial is 120. Yeah, it seems good to me. Let's go ahead and solve it. Accept this. Right. So back to the problem. Okay, so yeah. So when we are filled with these values, for this actually we have very limited scope, which means that we have used six distinct values. We have left with only three values here. And then if I come to this cell, this will also be having a very limited scope. This is having only three values which are accepted. And again, this is also having three values which are accepted. Right. So this entire grid, we can say that the way we fill these up, we can say that this is the scope for this, and this is right. So if I fill these values, I'm left with very limited options. So I can say that at the worst case, since these are filled when six values are filled, at the worst case there will be three inches here, right? So if I go with this, so this is probably, let's check if 3 to the power 81 is an acceptable case here or not. I know it will not be 3, even it is 2, it is very huge to be honest. Because let's say, let's call this 3 to the power 3 to the power 2, no, we cannot split like this. It's for 20, yeah, 20 ka power supply is also huge. This is clearly not a solution. Yeah, it is always fun to code a DP where there's a special configuration. So we have to convert this to a string, and this the map of string will be the state. And what will be the value of this? The value of this is what? Can it be solved? The moment it is solved, that is our answer, we can exit. But I'm really very unsure about the time complexity analysis. Yeah, this entire problem is now a time complexity analysis. So this can take 9 values for sure. This 8, 7, 6, 5, 4, 3, 2. But when we come to this cell, so it is left with 6 values at the worst case. This cell is left with 6. Case. Uh, yeah, and this part is guaranteed to be left with 3, 2, 1. And the moment we come here, we see 6 values over here. Right, so here also we are left with 3, 2, 1. The moment we come over here, we see that 6 values over here. There could be some commonalities which I'm not sure. So this can also take 3 to 1, and this can also take 3 to 1. It will be definitely less than these, but yeah, I think so. That uh, even if I talk about this is 9 factorial multiplied with 6 factorial, not 6 factorial, like 6, 5, 4, 3 factorial is 6. So this is 20, 127. 9 factorial is somewhat, let's call it 9 factorial. It was somewhat, let me check what it was. So this 8 factorial was actually, so multiply with 8, call it 50, 100,000. Multiply with 9 is 36. That is 3,60,000. 3 into 10 to the power 5 is just the 9 factorial. And when we multiply it with 720, it will be very huge, to be honest. It will go up to 10 to the power 7 or 10 to the power 8 at this moment itself. The next step will be like even if you multiply by 6, it will really shoot up, right? Uh, if I analyze the next cell, I can say that 3 values have been. For this cell, I might say that the worst can go up to 6 again. This is really a very used problem. I don't know, I think I need to check the hints so I can, because this is really hard. I have no approach coming to uh, acceptance rate is really good. This seems like a classical problem. Can I have the solution for this? Because really, this is really. If this is really brute force, then honestly, I don't know how to solve. Ouch. Let's check what people have put here. Leetcode editorial, Sudoku solver, beats 100%. You know what? I can see this editorial. There is a GitHub repository, which is really useful. If I say Leetcode solution GitHub, yeah. So I think, yep. Leetcode editorial solution, not Leetcode solution. Yeah, This is the repository which is really good. Maybe DMCA can take it down anytime, but we are lucky that this is currently available. So this problem number is 37. Wow, this is a very early problem, right? Let's go to the tutorial, problem data parser, it will screenshots. And here we go. So this is 37, right? And there's a pattern that Leetcode is actually, here we are. Leetcode is actually not changing the number of the questions. Okay, let's wait for it to load. First idea is to use brute force like we were thinking, guys. This is 9 to the power 81 operation. And then we have backtracking here. What is the backtracking? Backtracking is a part of recursion, right? The first one is called, there are two programming conceptions here which could have. The first one is called constraint programming. That basically means to put restrictions after each number placement. Yeah, that I was just thinking of. Like if I put 2 over here, we are left with 9 options. Yeah. I know this will help us to reduce, but how much? That's the thing, right? Complexity analysis is 9 factorial to the power 9. Okay. Oh, 9 to the power 81 is this number. Wow, they have calculated it. Wow, really cool, man. And this is very much less, right? So this was my second approach, right? What the heck? What the heck, man? If this solution is getting accepted, how is it often even optimized? Why won't will it give TLE, right? I have came to a solution where I had 10 to the power 27. Sorry, 27 to the power 27. So this is that solution, right? Like more or less, if we do a constraint PP here. But my question is that, like, how is this acceptable? How is this acceptable, man? So let me just check some solutions here, because this is really crazy, because normally 10 to the power 6 uh 10 to the power 6 is accepted in all the questions. Any value greater than 10 to the power 6 in order, like 10 to the power 7 or 10 to the power 8, will throw out a TLE, right? That's the standard like conceptions which we have. If I check what people have solved here, used here, oh, so this is exactly the brute, the same. Somebody has pasted the same editorial solution. Really crazy, man. This guy is really crazy. He's just taking the Leetcode screenshots and putting it in the question chat. Yeah, they have also copied this editorial image. Really crazy, man. So the time complexity of it is really huge. Uh, what are they doing here? I don't know. Somebody has also really, somebody has hard coded all the test cases. This is a hard code solution, right? Yeah. But let me check what is the time complexity. People are actually submitting this huge time complexity. I don't know. Okay, order 1 space and order 9M time. What is 9M? Got it. So intuition is here. Time complexity 9 to the power m, where m is the number of empty cells. So it could be 9 to the power 9. Really? Oh, sorry, 9 to the power 81. Are you really crazy? 9 to the power 81 is very much this. So you're not even using backtracking, right? That is also cool. Okay. So we use 27 sets here, 9 columns, 9 blocks, each showing 9 number. All of this is bounded by constants. So author 1. Piece complexity is not an issue here. I will just go to the problems and check what people are doing here. 9 to the power m, again copied solution. The bit mask optimization, what is the final result, bro? B to the power d, where 9 is the branching factor. This guy is really cool. This guy is really cool. So worst case is still exponential, right? So guys, this is really not fair, to be honest. Leetcode, you should specify that you are expecting a solution which is brute force here. I can also go ahead and code it up. So let's go ahead and try to code that up, because no, this is not the case. If somebody asks this question in the interview, then there you can talk, like you can also code this up. The coding part is really difficult. So I will just go with the coding solution here. And guys, that is the real exercise for this problem, that we will be coding this brute force, which is still hard. But it should mention that you should write the code which is not standard time limit bound. Okay. Did I miss anything here? Was it mentioned already? Chat, you can tell me if that is the case. I don't think anybody is watching it. Okay, now we are streaming for 47 minutes now, and we have come up with an approach. Oh, nice. So I will do a split live screen here. Uh, did I miss anything here? Was it mentioned already? So guys, I will be actually starting a new live stream where I will be solving this problem using brute force. So that will be more or less a very good video, because I post these videos later on. So let me start a new live stream. I'll be back in 1 minute, not more than that. Okay. Let me come here. Let me come here, and I'll talk to you guys with this part again.